the objectives of our lesson, it's time to configure routing services on the Cisco EasyVPN router. Our first step is to make sure we are allowing IPsec traffic into our VPN router. This router is probably an Internet Edge network element, which is an ideal position to provide access control services through firewalling. Most likely, this router is running some sort of firewall service, or at least access control lists, also known as ACLs, to implement anti-spoofing mechanisms and other security controls. IPsec traffic needs to be allowed through those security controls in the Internet-facing interface. This is done so the router can terminate IPsec VPN tunnels. There are different types of Cisco IOS firewalls. The classic firewall is based on ACLs, and it is the traditional approach to firewalling on a Cisco IOS router. The zone-based policy firewall is based on security zones. It is the more recent approach to implementing a firewall service in routers. It is important to identify which type of firewall we have in order to determine the component we need to change. Let's do this in our router R1, the perimeter router. To identify the firewall type, we can use any of the commands listed here. Remember, the show IP interface command and show access lists will tell you whether you are using and attaching ACLs to your interfaces. The Internet-facing interface in this example is the Fast Ethernet 0/1 interface. We can type show interface, and immediately we see there is an inbound ACL attached to the interface, conveniently called firewall inbound. This access list, which we can see using the show access lists command, seems to be allowing most of the protocols and traffic we need. Remember, you can identify its operation with the matches keyword for each of the lines of the ACL. This ACL could be part of a larger firewalling strategy. Again, there are two different types of firewalls. You can see the configuration of the zone-based firewall with a show zone pair security command. This one displays information on zone-based firewalls. We type it and see nothing. This means no zone-based firewalls are configured in this router. If you want to look at the classical firewall, the command is show IP inspect interfaces. Look at that. We do have a classical firewall configured in this router. That is where our firewall inbound ACL is coming from. There are inspection rules on our Internet-facing interface. Part of those rules regard the access lists involved in the access control process. We saw the access list. It is allowing most of our services, but we need to add the IPsec protocols and ports to it. After a little research, we find there are 4 necessary items. The first is protocol number 50, which is used for a component called Encapsulating Security Payload, ESP. Next is protocol 51, which is optional and may or may not be needed for a component called Authentication Header, AH. The third item is UDP port 500 for a component called Internet Security Association and Key Management Protocol, ISACAMP, sometimes also called IKE. The fourth and final necessary item is UDP port 4500 for NAT traversal, NAT-T. This is another IPsec service. Let's add those items to our ACL. It's an extended ACL called firewall-inbound. Let's add them at the beginning of the ACL. we will insert line 4, permit protocol 50. For the sake of simplicity, let's make the addresses any. We will also permit protocol 51, also UDP port 500, and UDP port 4500. We are all set. Our internet-facing interface is allowing the necessary ports and protocols. Our second step is to define the IP address pools for the remote connecting clients. Why do we need address pools for these users? Do they not already have IP addresses to begin with, which allow them to connect to the IP network? To answer these questions, we must remember how IPsec works. IPsec VPNs encapsulate private traffic within a larger packet to allow the packet to be routed across a public network. The private packet with private addressing can't be routed on a public network, but this is a virtual private network, so traffic needs to go between a private host and a private resource. The private host is virtual in a VPN. It is located outside the private network. The encapsulation process will use private addressing in the original encapsulated packet and public addressing for the outer encapsulation packet. The private address of the connecting host is typically assigned dynamically for flexibility, using either DHCP or IP address pools. In our example, we will use address pools, which must be carefully planned. It should be an unused address range in the network and follow best practices in address assignment. For instance, you should define it to be a summarizable address block, so it could be later easily and efficiently identified in ACLs and properly summarized by routing protocols. This address pool is created locally on the VPN router in our example, and later assigned to the VPN configuration. The local pool on the router is commonly used as a configuration alternative. Other options include DHCP servers sitting behind the router and VPN clients requesting addresses via DHCP. In that case, the router acts as a DHCP relay agent. AAA servers can also be used to provide a per-user or per-group address pool. The command we need is shown in the top right panel. IP local pool. Notice it will use a mask when the pool goes beyond classful boundaries. Let's configure it on the R1 router. We must give the pool a name because, to reiterate, we will later assign this name to the IPsec VPN configuration. Under the Cisco EasyVPN framework, you can have a separate local pool for different user profiles using the IPsec VPN. This allows for even greater flexibility in differentiating traffic from each user profile and applying different path, routing, or access policies to each profile. In our example, the security team is expecting a local pool called EasyVPN with an address definition of 10.254.254.1 through 10.254.254.254. Notice the use of numbers that are easy to identify, so administrators quickly know that these are remote access users, especially when they see source addresses within this range in routing tables, access lists, and other parts of the network configuration. At this point, we communicate with the VPN support team and request a change ticket so they can go in and configure this address pool into the IPsec VPN. They agree and deploy the change to R1. Our next step is to provide effective routing services. We need traffic coming from the VPN to be reachable from the internal network, especially for return traffic. The VPN subnets defined by the IP address pools are ephemeral. They appear and disappear as VPN clients connect and disconnect. However, they must be known to all routers in the internal network, or at least along the path of traffic flows that VPN clients will use. Several methods can be used to make the address pools known to routers in the internal network. The first method is perhaps the simplest approach. First, you select the address pool as a subnet of an existing physical segment. In the example here, the subnet 192.168.1.128 is a subnet of the 192.168.1 network. The advantages are that no additional subnets are needed, thereby reducing complexity and reducing the number of changes required to routers or routing protocols, because they already know the network. One disadvantage is that you must enable Proxy Address Resolution Protocol, Proxy ARP, in the VPN router's interface connecting to the segment containing the borrowed subnet. Other methods are more dynamic but require more complexity. They will designate a separate, non-overlapping subnet to be the address pool for remote access VPN clients. This requires advertising the subnet using routing protocols. A commonly used approach is the method known as reverse route injection. This protocol will inject the client's host address into the routing table, but only when that particular client is connected. If the client disconnects, the entry is removed from the routing table. You can then redistribute those entries in the routing protocol and the routes are advertised across the network. RRI is an IPsec feature, so we will not use it in this demonstration. Yet another method, shown in our top right panel, is part static and part dynamic. You simply create a static route, pointing to the remote access address pool, and then redistribute that particular static route in your routing protocol. This is the method we will use. Let's do it now. We know how to do this. We simply use the iproute command to configure static routes. If our IP address pool is the one shown in the previous command, then our iproute command is structured like this. Notice that we pointed to the VPN-facing interface. It's the one with the crypto map, and it will initiate and terminate VPNs. That's exactly the location of the VPN clients. Let's see which routing protocol we're using with the Show IP Protocols command. It looks like we are using EIGRP to advertise networks in our local area. We know that because the routing protocol is running toward internal networks, 10.6.6 and 10.6.7. With that, we should go into EIGRP and redistribute static. Best practices call for filters, so you only redistribute the static routes you want. It is also probably worth seeding the metric so it makes sense in the EIGRP domain. In order to verify this, we switch to R2 and display the routing table there. As you can see, the Show IP Route command shows us the remote access VPN subnet, 10.254.254.0. It is reachable in the routing table, and this works. As soon as VPN clients connect, R2 will know how to get back to them. Our next step is to tune NAT for proper VPN operations. As we discussed earlier, IPsec is an encrypted tunnel, in simple terms. It will encapsulate packets that use private addresses within the larger packet that uses public addressing in order to be routed across the public network. This edge router could be providing NAT services for internet traffic for hosts to acquire a public address. In fact, in our example, it is. To verify this, we can use, going back to R1, the show IP NAT statistics command. We can see that, yes, we have two inside interfaces pointing to the LAN and pointing to R2. We have the outside interface pointing to the internet. We also see that there is an ACL defining the networks we are going to translate. VPN traffic is not really internet traffic, right? It uses the internet, but it does not require a public address because it is intended to have a destination in the private network. Packets are processed in the router in a certain order, according to the services on the router. NAT is processed before IPsec encryption for outbound traffic. VPN traffic would be translated before it is sent through the tunnel. As we have just discussed, this is not only unnecessary, but it could also result in lost connectivity. The impact of this is that the NAT service needs to be tuned in order to bypass translation for VPN traffic. This VPN traffic is easily identifiable. You match it by looking at IP addresses and comparing them to the VPN address pool defined at the router. Let's configure the NAT bypass for VPN traffic now. We will use the same NAT commands we know, with a couple of additions. You can define the type of traffic to bypass by using either access lists or route maps. In any case, a permit line in the access list means translate. A deny line means do not translate. Let's look at the ACL, called NAT ACL. It is effectively translating all traffic coming from the local area network and going to any destination. We need to exclude the VPN destination so VPN traffic can bypass NAT. Let's do that. We'll use a route map, but first we need to build an ACL that denies the address pool destinations. Remember, a deny means do not translate when we finish configuring our new NAT rules. I'm going to build the ACL quickly. Access list 100 deny all IP traffic coming from any subnet of the local area network and going to our VPN address pool. Notice that we are using the VPN address pool as a destination. This is because the NAT configuration is relative to the view of the router, and for the router, the VPN clients are destinations because they are in the outside interface. It is also very important that we add another line to the ACL. Let's do that. We need to add this line to permit IP any. Why is this? Only VPN destinations should be bypassed. All other internet-bound traffic must be translated. If not, it doesn't work. It is a common mistake to forget this line. It causes a big impact in internet connectivity. The next step is to build our route map. We'll call it VPN traffic. And then we will permit the section that matches our ACL. We're now ready to apply the route map to our NAT configuration. Let's do that. In fact, let's remove the one we have now. And then do it again with a route map called VPN traffic. Associate it with our NAT pool and use overload to make it PAT, many to many. Okay, looks like we have bypassed VPN traffic from NAT, and we're ready to feed this to our IPsec configuration and see if it works. Let's do that.